in networks. And so we're going to go from everything from, if this were your basic stats class, we'd be doing everything from what is a variable to, multidimensional information, scaling. So we are covering the whole gamut today. And a lot of this is, really new stuff. And so some of it is going to be, it's covered in more depth than others. There's going to be holes that you're going to wish, like each person's going to find a bit they want, but they're going to wish they had a bunch more depth than they actually get. It's just the nature of the beast. There's just so much of this stuff to cover today. That said, we're going to do our best to provide things for you. I was hoping to have a whole thing on some of these new ERGM features ready today that I could sort of share as a workbook. It's not ready, so you'll get that. I'll post it on the DNAC website, hopefully sometime next week, but in the meantime, you'll at least get the ideas of what's there. We're going to start, like I said at the beginning, sort of modeling the what and why of networks, and then we're going to move through to a couple of special cases that I think people are particularly interested in, namely models for ego networks and bipartite networks. Then we're going to, after that, work on some things that have to do with simulations and things that have to do with dynamic peer influence models. And I can't remember what else the final ones are, but there's a whole set of them that's moving in. We're really pleased today to have a nice group of people that are going to help us today. So Carter is in the room, Sam is in the room. Where is David Schaefer is going to be here? He's not here yet, but we have a nice collection of folks. Tom Wolf is with the DNAC RA who's going to be presenting as well. And so there's lots of people that are working on this project. I like to think about this week as sort of my fantasy football team of everybody I get to bring in that I wish I had down the hall from me on any given day. And I can never bring as many in as I would like, but there we go. So there are no extracurriculars tonight. There is one sort of snafu that we discovered yesterday, which is that some people got parking tickets. If you got a parking ticket, but you got into the gate, that's because you didn't print out the thing, which we didn't realize you needed to print it out and leave it on your dash. If you got a ticket, let Madeline know, and we're going to do our best to make you whole. If you're parked down there now and didn't print out a hard copy, Madeline has printed out some hard copies, or Leanne printed out hard copies, Leanne printed out some hard copies. So you can run down and fix that situation now. But we do apologize if you found yourself in that situation. So, all right, any other snafus or issues? Great, so I'm going to go ahead and jump in. I'm going to just give this big, broad sort of overview. Try not to be too frightened by the fact that there's nearly 100 slides. Remember, I talk fast, so we're not going to get through all of this. A late addition, this is going to be a non-technical overview for those that go. So we're going to start with sort of broadly between graphs as dependent variables and graphs as independent variables. I'm going to spend the vast majority of my time sort of over here. I'm going to give sort of a brief into for where these things came from, a brief exit for what else you can do, and then really just a quick introduction of these bits, because this is what a lot of the later part of the day is going to be, is dealing on these kinds of models. So the pool you're about to jump in has its roots in this field known as random graph theory. And so there's a whole beautiful mathematical subfield of random graphs and the understanding of where random graphs come from. And then the thing, and we know, sort of we in the global sense of we, know a lot about random graphs. They're really well studied. And so if you think about these very simple random graphs, what we like to do then is think, well, we know all of these things about random graphs, but they're a crappy model of reality. So what we'd like to do is take everything we know about that and put a bunch of stuff in it to make it more like reality so that we can analyze the things that we do. And that's what the history of this field has largely been. So there's been new constraints on this notion of random graphs to create different kinds of models, different kinds of constraints on randomness. And those constraints then allow our models to fit better. And at the end of the day, sort of, you end up down in a series of models that people actually use nowadays, which are this broad class of P-star models or exponential random graph models, these stochastic block models, which I referred to the other day, which are categorical models for predicting networks, and then sort of the dependent variable side, which is these network autocorrelation models and trying to figure out where sort of networks come from. There's a little side path in this group that I love, which is called the bias network literature that John Skvorc has worked on, which we don't use much for inference in sort of this side, but if you're interested in thinking about the ways in which things move through networks in a non-random way, but systematically, that's a wonderful bit of literature to pull on. So anyway, that's a sort of Moody's map of where the statistical modeling world comes from. It may or may not be accurate to someone else's mental map, but it helps me think. We're going to talk in this presentation about these little bits, and so that's where we're going to go. So there's a lot of things that we're going to get to later. Now, this is a vast literature, and so if you want to learn more about it, what I strongly encourage you to do is to go and read some of these papers and some of these projects. And so one of the things that there's a wonderful book by Lusher, Koshin, and Gary Robinson, that this is a really nice piece on the background of exponential random graph models. If you really want to get into the details of the wider sort of work on statistical analysis of graphs, this book is great. It's like you're going to go in the deep dive, right? So this is a technical treatment of this work, and so I highly recommend it. But it's it's not light beach reading. For those of you that want a slightly more light beach reading, we have a nice, I think, collection of work in our handbook that came out a couple years ago. This sort of starts with like what it is you should do, and so Philip has a nice sort of decision tree of what kind of model you should use under which kind of situation, which is really nice for what kind of data. And then a whole set of papers that describe the ways in which you might use each of these models and how you interpret them and so forth. So I think those are nice. And then there's just a dizzying array of papers coming out every day. So I really encourage you to find some of those, and you'll see links to them throughout this presentation. The only problem with the Oxford Handbook, despite what Pat Dorian said, because he wasn't cited, the only problem really with this particular book is that it costs too much. So if you would like one of these chapters and can't get it because your library doesn't have an electronic access to this one, send me an email. I can get you a copy of the chapters, so that would happen. All right. So what do we mean for this particular set? So network inference problems are a little bit different than your standard statistical inference problem. The standard Sociology 101 statistical inference problem is to say I've sampled a set of cats, and I want to know if the cats that I've sampled actually look like the population of cats in the world. Right? And so you have some distribution of orange cats, tabby cats, and white cats, and you want to know if that matches the population's distribution of orange cats, tabby cats, and white cats. That's not the world that we live in networks, because the first assumption of networks, usually, with the big asterisk for ego networks, but for sociocentric networks, we by assumption have the population, or at least a really good chunk of the population. So you're not inferring from a sample to the world at large. Instead, what you're inferring is from your realization of the world, the plausible set of realizations that could have been generated under this sort of reality we live in. And so it's a slightly different inference problem. So it's not an inference to the population distribution, it's an inference to the relational class of things you're trying to play with. What that means practically for us usually is the distribution, the graph we've observed, non-random, right? Could we account for this graph by a purely random process, or is there something systematic? Because the kind of questions we're usually interested in are things like, do men hang out with men more often than they hang out with women? Do people who talk about drugs also talk about sex? And so these kinds of questions, we can compare them to some sort of a baseline, and that baseline, the obvious sort of non-stupid baseline, is to flip a coin a bunch of times and see if we would have gotten the same answer. And the logic of that is if you would have gotten the same answer, then there's no generative social process that's creating the patterns you see. It's just random noise. And if you've ever stared at tea leaves, you know that humans are really good at picking out patterns from random noise. And so this is actually a very nice null to be able to compare to. So how do we do this? And if we want to compare our observed network to some network sort of distribution in the world, what you would like to do is say we have observed a graph. and let's compare it to all possible graphs that match on the key features, like the number of edges in that network. The problem with that matching process is the number of possible graphs you need to compare to is really, really, really big. And even if you have a very small network, only 10 nodes, you can get many, many orders of magnitude of the number of possible graphs you could be looking at. And so from a pure computational standpoint, this is really impossible. And so you're never going to really enumerate all the graphs and see where your graph fits. Instead, you're going to generate a process that creates graphs that look representative of this distribution. That's a hard thing to do. And so that's where a lot of this work has gone. So stepping back to the simple side, if you know sort of a process on your graph, and this is where the beauty of a lot of the random graph stuff comes from, you can sort of generate graphs that are good representations. And so the simplest, of course, is just a simple Erdos-Randi graph. In an Erdos-Randi random graph, each edge has a fixed probability of being on or off. You flip a coin, you get a draw from that distribution. You do that a bunch of times, you'll get a distribution of graphs, right? And this is just one draw of a simple Erdos-Randi graph. And if I were an ethnographer, I could tell you stories about why this person is important and why this person is peripheral, but this is just a random graph, right? So there's nothing real here. Now, like I said before, there's a lot we can learn from random graphs. Random graphs have really nice properties that are well known, things like the emergence of a giant component, that if you have a certain number of ties on average for each person in the network, and they're distributed randomly, then you go from the graph being a bunch of little pieces and over a short distance to it being largely connected. And if you shift the shape of that random graph, this distribution, this kind of a threshold model actually still holds. It's just where the threshold is shifts and the steepness shifts, right? Now you can construct graphs where it doesn't hold, right? We can like railroad networks, for example, but those tend to be very different from the random network. So once we realize that simple random graphs are very poor models for real life, we want to figure out some way in which we can constrain that randomness so we get all the beauty of the random graph models, all those things we can know about it, but it better represents the sort of null model for the world we're looking at. And so the way we do that is we make the graphs a little less random. And so you can imagine, for example, saying, well, I know that in my network I have three types of people. I have white people, black people, and other people, because we don't collect data well on other people in the settings. And so what I might say is, well, what I really have instead of one random graph is that I have 9 random graphs, right? I have one random graph of the white to white ties, one to the black to black ties, and one to the others and others, and then other random graphs that describe each of the bits and pieces before. And so I can partition my network into a set of risk sets and then say, well, in each of these, there's a coin flip that says about 9 times out of 1,000, about 8 times out of 1,000, and about 6 times out of 1,000 we would expect to see a heads, whereas over here it's only 1 time out of 1,000 we'd expect to see a heads. And so we just flip a coin like this, and that gives us a random graph that will match the observed distribution, the observed volume of ties within and between groups, right? And so that's a nice thing to do. You can do that. Then you can ask, does a graph where I do this, where I take that little exercise and I flip the coins the way I say I'm going to, if I do that, do I get something that looks like the real network? And it turns out, no, not particularly, right? So in this case, right, what we can conclude from that is that if this is what the real network looks like, and then I do this simulation little exercise or this random graph exercise where I say, let's make sure I can match it on the mixing matrix, if it doesn't match, that means that the mixing itself can't account for the graph, right? That means there's some other social process generating this network above and beyond just the race mixing. It doesn't mean that race mixing doesn't matter. It just means that a race mixing is not in itself sufficient to account for the patterns we observe in the graph. And so, for example, you might see that we could look at something like the degree distribution. And so the observed degree distribution is much more skewed than what you get out of that simple random process, even once I've constrained mixing. So I might need to add some more constraints to get this to happen. And that's the basic trick we're doing, right? So at the end of the day, all of the models we're going to discuss today, well, all the models of graphs, have some kind of this flavor, where you've taken the space of all possible random graphs out there that you could compare your observed graphs to, and you've constrained that space in a systematic way and asked, does it match the graph I've observed? And the hypothesis here, or the assumption of these models, is that by doing that, you fit your data to the model. And so it's a reasonable conclusion that the data you drew came from the process defined by that model. Now, this is a subtly different thing than what you and I normally do when we're trying to say whether or not, a social index predicts an outcome. We're used to doing a rejection of a null hypothesis. So we reject the hypothesis that there's a correlation between education and income, and we see that, in fact, we can't reject that hypothesis. What we're doing here is we're confirming a hypothesis in some ways. We're building in a model to account for the graph that we've met. And you can nicely say that things don't match the graph that you've produced, right? So there is a rejection sense. So it might be that the feature that I'm finding, there is no connection between people above what you'd expect by random. So there is an element of this. But from the graph as a whole standpoint, from a fitting function standpoint, you have to always keep in the back of your mind that what you're really doing is a very complex version of asking if all the numbers you've arrayed sum to the number you fit. And you have to remember there are lots of different numbers that could sum to the same number, right? So it could be that the thing that's driving this feature, right, isn't really race mixing, but it might be music preferences. And if music preferences are really highly correlated with race, and if that's the case, then a race mixing model matches, but a different model that used something like music would fit just as well, if not better. And there might be 100 other things that could fit just as well, or if not better. And so you got to be really careful. That's not a statistical problem, that's a theory problem. And you just have to be aware that what you're fitting is built on, it's a theory that you're proposing, and you're saying that my theory matches my data, but it might be some other theory could also match this data. And so then you would need a test case to distinguish those two. Okay? So the basic idea is that if this helps a little bit, then we might do it a little more. So we might say that instead of matching on race, I match on race and gender. And I say, okay, now I'm going to fit, instead of fitting 9 cells to my mixing matrix, I'm going to fit whatever this is, 8 times 8, so 64 cells to my mixing matrix, right? And then I might say, well, if that works, let's find age within gender within race or something, right? And so I can get more, tiny cells. And at some point you realize that that's really a pain in the ass, and so what you might do instead is say, let's fit a distance between people, right? And so I can say instead, if I could just identify the proper way that makes me similar to Carter and how the two of us are different than Gabe, we could place ourselves in a low-dimensional space and say that the likelihood of us having a tie is really highly correlated with where we fit in this space. And if we get really lucky in how we fit this model, we'll be able to do that nicely, right? And so this is the logic of the model. It turns out that some things you can't turn into a distance, or at least it's not natural to turn them into a distance, and so you would rather treat them as categorical, and so you might have sort of multiple dimensions of this kind of thing where you stack them on top of each other. But that's the logic of the idea, is that we try to constrain the space to identify ways in which we can get from this kind of coarse mixing to something much more fine. And it turns out that this notion of doing a space or distance model is the logic behind latent space models. And so there's a whole class of models in the network literature called latent space approaches. And what they're literally doing is trying to infer from the pattern of ties a set of metrics that we can create a distance score on. And so the way this works is that we say that the probability of observing the graph that we've observed as a function of some distance scores and some other observed variables is a feature of their distance with each other. And so that probability comes out to say that the further we are apart on this, the less likely we are to be tied. The closer we are on this distance space, the more likely we are to be tied. And intuitively, the thing that makes these really cool is that we don't know what these Z's are ahead of time. Right? These aren't things that we just are given to us like education or income. They're things that we let the tool find for us. And so the latent net figure, this is done on the Samson Monastery data. You're going to see a lot of the Samson Monastery data today because it's small and it's easy to run some of these things on. But you can fit, for example, the two-dimensional model. And the nice thing about the model that Hoff and Hancock and others have done with this, in this Bayesian framework is that the positions in this latent space are assumed to be noisy. So you don't assume you have a perfect fit. You get a cloud of points in those areas, and you can ask how likely it is that you've hit that particular set. The nice thing that they've done in a lot of these models is that they've said not only is it the case that we're fitting in the z dimension for how many numbers of dimensions you want, but you can also overlay groups in these dimensions. And so you can say that it's not that the distance between myself and Carter is essentially on a somewhat different metric between myself and my wife, right? We have a different logic that drives our connection compared to a Carter and Meissen connection. And so those connections might need to be fit in a different sort of underlying adjustment to the scaling. And then you can do that well by saying there's a third feature here, a group variable, and the number of groups in your model allows you to fit. So this is combining this notion of a stochastic block model idea that we talked about yesterday with this notion of a latent space. Questions, comments thus far? Is this reasonably intuitive? Okay. All right, and you can do this in lots of ways, and I love these latent space models. I think they're a lot of fun. The problem, and I'm going to make a claim, and I think someone else should jump in, like Carter or Sam, you should correct me if you have different opinions. But the beauty of a latent space model, and the reason that they're really valuable, is that they're sort of information preserving and ignorance robust, right? So if I don't know anything about what's generating my setting, the machine will find a pattern that fits it well. And that pattern that fits it well is something that I can use. And this is particularly useful if your network is a nuisance. So if you have network data and you have all these connections between people, but you don't really care what's driving those connections. What you care about is whether or not, say, your program intervention worked, but you know that all these kids are contaminated with each other in the latent space, then I can fit a latent space model, I can correct, I can identify where people are, and I can use that as a control for whether or not my intervention worked, right? And so it's a nice way of summarizing the network in the face of ignorance. It's also a nice way to do exploratory analysis. It tells you that this blue cluster up here, there's something uniting them, and I might not know what it is, but I can go up here and find my data and say, well, what correlates well with this Z statistic? And that might help me learn something about my setting. What it doesn't do is say that there's a generative process, right? So the Z's are an outcome of the pattern of ties, and they're hypothesized constructs that generate the network. They're not something that's live in actors' heads. Is that a fair statement?
I haven't. I was born with everything is like one of my mom's friends said when I was a child, that person was right. I think it's a reasonable statement. I think the issue is just, you always, with any modeling framework, you have to know what you're going to do with it. And I think that's the question that's relevant to like space models and every other model. So what do you want to know? If you want to take your highly complicated network and you want to map it into a couple of dimensions and you want to be able to think about it in that way, that is one of the approaches to doing that. And if that's helpful to you, then fantastic. And I think sometimes it is. But of course, it's not innocent. Like that mapping does have assumptions built into it, and you don't know what they are. Well, I know something what they are, but they're very subtle. So, for instance, you're putting constraints implicitly on the what's called the graph spectrum, so the eigenvalue of the graph. And if you're not familiar with what that is, then don't be surprised because most people aren't, right? But that's shaping what your network is, and it's coming out of hidden assumptions in that model. So it makes it, for instance, be dominated by core periphery structure. It tends to suppress bipartitions. And is that good or bad? Well, that might depend on what you're looking at. But so I think the downside of these things is that they are somewhat opaque. And at the end of the day, in the worst case scenario, you're going to map it as complicated as your territory. You took a network you didn't understand, and congratulations, you made it into a bunch of points that you understand. Now you're winning. But sometimes that is winning, because there might be things you know what to do once you have coordinates. Now there might be things that you can do with those that you didn't know how to do with the graph. So sometimes that is a win, or people are using them as parts of other models. So I think I'm sounding really negative about latent space models, but I think they are really interesting. But you always have to be able to ask this oracle question, right? Imagine that you had the oracle and you could ask her, to give you the answer to your analysis, and she would hand it to you. So the oracle question is, what would you do if she gave you the data or she gave you the answer, right? And if you can't answer the question, what would I do with the answer if the oracle gave it to me? then it's not going to help to ask the model, because the model is going to give you, at best case, she'll give you what the Oracle would give you, and you don't know what to do with it, you have a problem. So I think that's always the question with any modeling framework. It's not unique. But I think for latent space, you really want to think hard about the Oracle question. And what do I want to know? And if I had an Oracle that could give me a k-dimensional vector representation of my graph, do I know what I would do with that? And if you're like, yes, if only I had that, I would be able to do something really cool, then this can be a very helpful framework. If you're like, well, actually, now I think about it, I have no idea what I would do with it. Well, then, maybe this isn't going to solve your problem. Although, I agree with the exploratory sentiment. Sometimes you don't know what you're going to do until you look at the data, and you really need something to reveal structure in the data, and this can be one of many ways to reveal structure. And once you look at what's really going on, now you may realize, oh, okay, I need to build a more confirmatory model that does X. Now when I look at this. So if it's a useful device for discovery, that can be very helpful as well. But I just think the big challenge with all latent variable methods, not special to this one, is that they can be enormously powerful. I use latent variable methods all the time in exploratory work. But you really have to, it puts the onus on you to think about, what do I want? What am I going to do with the answer if I get it? What is it going to mean? What properties do I need it to have? And I think that's the key question. I think a place where people could get lost in latent space models is that they don't really know what they're going to do with those positions, right? Or they think the positions are magical. They're just a re-expression of your network in those before. As long as you keep that in mind. So
oh no, that's great. That's perfect.
This might be oversimplification, but is this like an end to doing for vector analysis?
yes, absolutely.
That's exactly right.
In fact, like, it's not only is it so much like that, but one of the, so if you go back, you have Peter Haas' paper up there. One of the variants that actually is a whole lot of work that's done on that, although in the social network we don't use it as much. There's another version of this whole latent factor model, which the structure behind it is multiplicative, and it is exactly the same kind of math as factor analysis, where you're in essence saying, I'm going to assume people have latent attributes, and then their propensity to be tied is due to mixing on those attributes, exactly like what Jim was showing with manifest variable, but now with latent factors. And so the spatial version is similar, except that instead of it being, a multiplying my value by your value, now it's distance in a space, and those are closely related concepts. So you can do exactly what you say, and in fact, there's a whole lot of variant literature, some very complicated models. You can have, infinite latent feature models if you're not satisfied with a finite number. There's all kinds of these things. And all of them are trying to say, is there a way I could explain in a way, or represent the structure of the graph by imagine there's a whole bunch of hidden variables that describe attributes, and it's all about mixing. And so yes, you can totally think about it in that way. And in the same way that like when a factor analysis kind of way of thinking could be helpful, but now for who's tied to whom, these models can be helpful. When having hidden variables that you don't know what they mean is not helpful, these models will not be helpful. So I think that's a very good way to look at it. And if you're familiar with things like factor analysis or PCA or the like, and in a general way of thinking about how to use them, I think the same kind of spirit applies to this.
And that is all we're going to talk about latent variables for now. So this is why I wanted to get it going, is because it's right there. There you go. No, I like that. That's awesome. So the alternative sort of approach is this what's come to be known as exponential random graph models, which was originally known as P-star models. In one of those chapters in the handbook, Stan gets a little annoyed at the model naming framework, but there we have it. So the thing that is stuck are ERGMs. And I want to give you a little bit of intuition by virtue of a dyad model of where this comes from, and then tell you why that model is wrong. But I think it's a nice way to get a little bit of intuition. So effectively what we're often trying to do when we're trying to model a network is that we say we have this, this two-dimensional array of zeros and ones. And it's sorted nicely because it's an adjacency matrix of froms to twos. And we know that we've observed one set of this. And we are ignoring the diagonal because we don't care about self-ties in this particular case. But we have some ties that are off and some ties that are on. And if we had the oracle would say, look, all the probability mass on the zeros is 0, and the probability mass on the 1 is 1, and you could fit your model perfectly. And we don't have that. We have something else. And so what we have is our intuition about what might matter. And so what we'd like to do is say, well, what's the best way to fit this set? What are the things that we can do? What's the information we can draw from to fit this set? And there's a couple of original ideas that are pretty straightforward. And so the first thing you could do is say, well, I have no idea what fits this set, so I'm just going to flip the right number of coins, right? And what that says is I'm going to add a parameter, which is the number of edges in the model. It is an intercept. And what that does to the space of prediction probabilities is it says everybody in the network, every possible edge is equiprobable, right? So that's all this is saying. It's just saying density. And so it doesn't fit particularly well, right? But it does say that it's not 0. Right, and so it's your intercept in these kinds of models is almost always going to be negative because this is on a logit scale. And so what this does is minus 1.3 exponentiated comes out to 0.24, and that ends up being what you're looking for, right? So that's all fine. There we go. That's not particularly informative, and so we say, well, what else can we know about this network? Well, we might say that there are row effects, that we recognize that people differ in their likelihood to send ties to other people in this network. And so, for example, in this case, we see that these dark blue rows, everybody sends 1 tie, then a little bit more in the 2s, a little bit more in the 3s. The pinks are 4, and this guy sends 5, right? And so now what we say is that we just have a row-dominant model. Each person in the row gets to predict that we have a baseline number of ties that everyone does, and then an adjustment for the number of ties that differentiate each row from every other row. And that then does exactly what you would expect, right? What it says is that now instead of having a constant density in this matrix, we have a slightly higher likelihood of finding ties in this row than we find in this row and so forth. But notice we miss all the columns, right? So it's still uniform across all the columns. So we might go, well, that doesn't seem right, so let's fit the columns. And we could do that, and we'd have the same kind of problem, right? And so you would have in this case that we fit the right probability of the number of ties that fit in the column. And we see that there are some people that are more popular than others and so forth. Well, the obvious non-stupid thing to do next is to fit both the rows and the columns, right? And so now we're getting somewhere. Now we say, okay, well, if by random chance alone, we see that these 3 cells have a really high likelihood of being hit. And in fact, the bolded ones are the ones that are true in that first matrix. You can see that we actually did pretty good here, right? So we hit those ones that we expected to hit. We hit that one. But you'll also see that we have relatively high probability mass on some of these things that don't matter, right? So we wouldn't expect these ones to fit, or these ones didn't fit, but by volume they would. So there's something pushing these folks away from having a tie here. So we're clearly not fitting everything that we could fit in this model. But in this, because it's a made-up model, there's lots of things that this thing does for us. And so that's part of what's there. So we might then imagine that there's some other magic quality variable, which would be something that has to do with a dyadic feature, such as whether or not we're both the same race or like the same music or have beards, right? So these are the kinds of things that we might put into whatever Q is, and it's a function of I and J, so it's a dyadic feature. And so this is an observed variable that says that how similar we are, how distant we are. I just made this up to fit nicely. And so you can see in this case now that we predict a very high probabilities for some of these ties. And so this does a really nice job because we had good theory in this case of what predicted this tie, i.e. I knew the way I made up the data. And so that makes it work nicely. But that's the logic of what we're going to try to do when we build these models. We're going to say there's some feature of the structure of the graphs. In this case, I just used the rows and columns. But we might also have functions on the dyad. So the number of third parties that we have in common is a kind of a dyadic feature. The number of attributes that we have in common, those are the type of dyadic features. These are things that differentiate one dyad from another. And that's a feature that allows us to fit the model. Right? Now, it turns out, of course, that the model misses in some cases and hits in others, and that's that's the way the world works. And if it's a good model, when it misses, right, you have to figure out why. We miss because it's either a poor model or a poor model estimation, and in both of those things can be happening. And so the goal is to fix that. So the twist, however, and the reason, and you could do all of this with a simple logistic regression, right? So that's possible. The problem is that we're not actually interested in dyads. What we're interested in is whether or not the entire graph, the entire network object is a representative piece from the distribution of possible networks of that class, right? And we operationalize it as these features of the rows and columns and dyads on the network, right? And so what that means subtly is that the kind of intuition we get from logistic regression is good for thinking about effects, but it's not good for thinking about inference. And so for thinking about inference, we need a different type of model. And that's what really a lot of the work in this field has been doing for a long time, is to figure out what determines the underlying inference. And the way to do that is you need to have this little critter here. And so what we're saying, this is the generalized formula for the exponential random graph models. And we're saying the probability of observing the graph that I have from the class of all possible graphs like this is a function of a set of parameters and a set of summary statistics that is normalized by the type of graph defined by those parameters. Right? And this little normalizing constant is the thing that's difficult to do. Now, it turns out there's some nice work that was done way back in the day. I don't remember when this paper was published. The original BSEG paper was in the 70s, right? Something like that.
BSAG,
What's that?
BSAG?
Yeah.
This stuff is 74, so
Yeah.
there were two papers, 70%.
But what was nice about this work is that because this is that big denominator I showed in the first slide that had that exponential growth idea, is that the number here is so big you can't really enumerate it. And so you need some way to get simpler. And what you can do instead, it turns out, with a little clever trick, is you can use what are known as change statistics. So you can take whatever statistic you have that you care about, and then you take the difference on them. And that does a nice job of giving you the conditional probability of that tie holding the rest of the graph constant. And that feature, it turns out, is a nice way to get your estimates of your thetas, which is the thing you ultimately want. So the steps to doing this then, in the general non-technical sense, is you want to specify your model, you want to fit the model, you want to examine whether or not so then you have these two problems of whether it's a poor fit. Is it because the estimation problem is bad or the model specification is bad? If the estimation is bad, you can test that with these things called MC-IMCHI chains, and so you can figure out if your chains converged and all these kinds of diagnostics that are for that. And then you can figure out the substantive question of whether or not your data actually fits actually matches the distribution that your model says it does. If poor, you return to 1 and you just do this loop over and over and over again. And if not, you publish your paper and get tenure and go home. So that's the way we work it, right? So that's the goal that we're trying to get to. And thankfully, the process of doing this doesn't require you as an individual to sit down and write a bunch of these change statistics on your computer one by one. Because Carter and his team and a bunch of other people, starting with the StatNet group, have done this for us. And this is the exponential random graph term set in the StatNet package. And the StatNet package, boy, I think the first version of this was early 2000s, something like this. It's been going on about 20 years now. Martina Morris, Mark Hancock were sort of the original sort of pushes on this. Then with Carter, I had a very minor role at the beginning of this bit, and it was really nice to sort of see this process go. And the way it sort of developed was once this recognition came about that you could fit the models with these kinds of logistic regression-like terms, and then correct some of the problems with the logit models with the Monte Carlo simulation models, sort of the floodgate opened. Because what we discovered, or what they discovered, was that there's lots of different ways you can specify. There's lots of things that are relatively straightforward to specify these. And so this generalized formula allows us to create many, many different terms. And so you can take in theory, any statistic you care about on the graph. Maybe I'm interested in the number of unbalanced cliques of size 5, right? That would be a really strange theory, but if I wanted it, I could do it. And in theory, you could put the exchange statistic in. That would be a really expensive one to calculate, but you could do it. But instead, thankfully, the team has put together a whole series of these different terms. And if you go to the ERGM references packages, you can find these terms. There are now hundreds of terms already built in, and there are a handful of terms that different people have built for specific questions. So Jeff Smith, a former post-PhD student here at Duke, who's now at the University of Nebraska, built a nice ERGM term for the tau statistic, which is a Eugene Johnson's hierarchical score summaries. Right? So there are features like this that you can build on your own if you want to put in, or you can take different characteristics that are built in there. I'm going to use some very cartoon examples of what some of these might look like, sort of the broad classes of them. So there are a whole series of properties that have to do with homophily, right, which are the things sociologists care about. And these are node match characteristics or node factor characteristics or mixing matrix characteristics. They all have to do with essentially the extent to which like goes with like, or people of one type complement another. And so there's a whole set of different terms that fit into that. An example is node match. There are a series of social balance terms or hierarchy terms. These have to do with configurations of patterns within the network. It turns out that there's a very fundamental difference between these kinds of characteristics and these kinds of characteristics, which is known as dyadic independence. These kinds of characteristics are actually really easy to fit in various. They behave very nicely because when you do that little change score on one dyad, it doesn't fuck with the rest of the graph. But when you do it on these, it does. And so this is where you need to think about these. And it turns out that the kinds of inference we can do using a logit model on this are exactly right, and on this are highly suspect. And so, though maybe not highly suspect, often suspect might be a better answer. Then we have different kinds of larger scale parameters we can fit, right? So we might think about clustering and other kinds of k-paths that you could do. So you can have whether or not it's likely that people send more ties out or in, or whether they're a certain length or so forth. We have in degree and out degree parameters and other kinds of star parameters that you can fit that are all getting at sort of structure of the network. There is thankfully now a large body of established practice in the field for fitting single layer binary ERGMs. And so it's good to start with some of those published models, figure out why they used those models, and do the same thing before you go off and just do your own, sort of write your own script, but that's the idea. There are a couple of things to keep in mind. And so one of the things that I've been sort of harping at this idea that the model is not just a logit model. And that's because these models behave a little differently than the kind of general linear model many of us are used to playing with. And in particular, OLS is remarkably forgiving to bad model specification, right? So I can fit a linear probability model. It's nice to interpret those models. It doesn't have some of the hairy bits that go with interpreting a log odds on a weird scale, right? So you can do that, and you can publish papers in Econometrica and be fine, and everybody's happy with it. Even though we know the model is wrong, it tends to be useful and robust, right? These models think that, in fact, because they have these non-independent features, because they have features on one edge affect features on another edge, which can affect features on another edge, the model specification really matters. And the best example of this came up with a set of ideas that came around fitting social balance rules of triangles to networks. And so our intuitive sort of sloppy theoretical sociology sort of approach to things would say that we expect social networks to be balanced. So we expect that if a friend of a friend is a friend, that we'd have a positive association between the number of triangles in the graph and the probability of seeing a tie. And so this is OLS, right? The more education you get, the more richer you are. And we just fit a term to it and call it a day and go home. The problem is if you do this exact model, if you just fit the number of triangles, what you're actually telling the software, what you're telling the process, is that this is good, right? One triad is good, and that's good. Then that must mean a few more would be better, because that's what this curve says, right? The more triads, the better, right? And so what it's going to do is it's going to keep adding arcs until it runs out of arcs based on your set, and it's going to do it in a way that maximizes the number of triads. And so what you're always going to get, or what you're often going to get, are bunches of little cliques, or one big clique and a bunch of isolates, and over and over and over again, you're going to think, well, this model sucks. And by inference, you're going to say, this software sucks, because I do this in OLS and it works fine. But it turns out that your theory is just bad, right? What you really want to say is it's not the case that everybody is friends with everybody. A friend of a friend is not a friend. That theory is wrong, right? A friend of a friend is an acquaintance, and a friend of most friends are friends. And so there's a wonderful sort of a book by John Levy Martin on Networks from Social Structure, I think is the title of the book, where he goes through some of these folk theories and says, imagine that was actually true. So imagine it was the case that a friend is a friend is a friend, right? Like, you wouldn't want to actually live in that world, right? Because somebody's a friend with your racist uncle, right? And you're probably a friend with them, and you're a friend with them. And so we know what that would look like, right? You would have these tight cliques and clans, and it's socially incomprehensible. We can't do that. And so in fact, what the theory should be is that a set of close ties of friends if friends are true. But once you get out a certain distance, the marginal return to new friends is pretty low. And there's some number of terms, and this feature here, this sort of diminishing marginal returns, is the way that people actually work in the world. And if you fit, instead of triangles, the number of, I should have changed out this term, I didn't have it set there. If you were to change this out to something like the geometrically weighted edgewise shared partners, this is the geometrically weighting part, it's telling you that, in fact, this is a diminishing marginal return. Right? And so this is a better specification. Now, this is the clearest version, or one of the earliest versions of where this problem, and you'll hear this problem referred to in the literature as degeneracy, which is, I think it's for many of us who work in the health field that's not the best term because degenerate means something specific and is not particularly nice. But anyway, the idea is this model collapses, right? It falls apart in various ways. And so we want to think about ways that better specify it. And if you find yourself fitting these models, and you then do the goodness of fit part of it, and you try to figure out where things are at, and your model just doesn't work, right? You might think very carefully about this kind of general specification problem. Is the theory you're fitting actually like this? And it can often be the case that you can do better than that. All right. So that was a very non-technical, quick introduction to the process we're engaged in. And it's a reminder for many of you, and perhaps new to a few of you. And so what's happened from that first set of quick, maybe I should stop there quick and see if there's any basic questions on the foundation bits before I jump into some of the new bits. All right, so it turns out then, like I said, that idea is 20 years old. The GWESP idea is maybe 15 years old, but the field of these models, the generalizability of these models has just exploded, right? So there's now lots of different ways that you can do that. The original models were for binary, network data, and we've now in the cross-section. And so now the field has generalized these in really remarkable ways. And so there's a whole set now of work that's being done on the dynamics of these models. So you can ask not just whether a tie is present or absent, but whether a tie emerges or disappears, and whether that does so conditional on features in the graph. And there are a whole array of these different types. David Schaefer and Scott Duxbury are going to talk about those later today. Relational events models. Carter is the inventor of these models, or for our networks, not just of social relationships, which are thought to have some kind of durability, but activity on those relationships, like a phone call or a radio call or something like this. And so these sort of events that occur on networks happen off the same kind of a similar kind of logic. It's been extended now to bipartite networks and ego networks, and so you can imagine fitting these networks to collections of small graphs, and that's the ego network side of things, or to networks that it's not necessarily possible for each person to link directly to every other person. And so Tom's going to talk about those two kind of models next. What I'm going to do is talk a little bit about some of the new tools that have come into the software that you might not be necessarily aware of, but I think you might find useful. And so it's going to be a very high level description of what these things are and where they go. Okay? I have a couple slides here. This is really just my way of fitting in a plug to Scott's book, so go buy his book. I think you would like it. And there's also a great temporal tutorial on the StatNet page for that as well. All right. So what are the new things that the tool has built in the last few years? I called it ERGM 4.0, but I think we're now up to 4.4 or something like this. So the thing has gone, it keeps developing quickly. The first thing that's different from the original specification is a whole new way to specify models on the fly in a way that you might be used to doing when you do fit general linear models. So instead of having to code white male, black male, white male, black male, as a separate variable, you can now cross those two characteristics dynamically as you specify the model. So it's much more flexible. And there's lots of different ways to do this. And so you can do sort of string searches. You can do string pattern searches. You can specify, and I'll show a couple examples of this one. You can specify a whole series of different functions on the graph. So if you want to put polynomials, for example, or squared terms, as you would if you wanted to do race and race squared, or income and income squared. Race squared doesn't make any sense. And there you can also specify formulas. And there's also this nice feature here, because these things can be combined. You can say, find the thing, the identity of, identify 0, 1, the things that are whatever's in there, and whatever's in there could be functions of these characters, right? So so these things cross-load in very nice ways that make it really flexible to do things. So for example, I might say that I want to fit to whatever network I have a term for the edges and a node covariate, which says that I'm asking whether or not one of those row or column kind of effects. So a node covariate based on the grade. This is a school network. And I think that that term differs whether you're sort of as a curvilinear. So it might have a peak that maybe, it's a case that 7th graders and seniors are less engaged than our sophomores or something. And so that would say, let's fit it with grade and grade squared. You could do it this way. You can also do it this way. But notice that I don't have grade squared in my data set. That just happens to be something I'm calculating on the fly. If you do that, you get the grade as you would like. I didn't have the result there. That's too bad. It's a silly result, but there it is. The other thing you can do is you can pipe in any kind of feature that you're used to doing. And there are a handful of these that are built into the software, such as largest and smallest, and is in, I think, is the other range. Look at the documentation. It shows you what is there. But it's just to let you know that you can say, let's take the levels of grade, and I'm going to take the 2 smallest grades. So in this particular data set, there's just a handful of people who are in grades 11 and 12. And so those are the smallest ones. And so let's take those 2 smallest ones and call them number 99. So now we get a node factor for 8th graders, 9th graders, 10th graders, and 11th and 12th graders are fit in here. Right? So that's just a simple way to combine them. And you can see that they don't differ much from the overall edges attribute. Again, a bunch of different things you can do now, which I think are kind of nice. You can filter things out. So I can say that I'm going to only take a certain subset of my edges. So I might only, when I pull in my network, I only want to look at ties say for amongst seniors or amongst juniors or something like this. You can treat a directed term as undirected. And this is a nice feature if you want to ask whether or not a lot of these things, effectively what you can do is fit sort of pseudo interactions. They let you specify different subsets of the data and treat it as a separate piece. But what's nice about this is that you can do this to terms specifically. So you don't have to symmetricize your entire data. You can say that I want to treat transitivity as if it were ignoring direction. So I'm going to just look at closed triangles, but I'm going to ignore the direction, so I can use that here. And the formula rule idea is that these are the rules you can use. So it's a weak symmetricization says that if I nominate you or you nominate me, call it a tie. A strong says if I nominate you and you nominate me, call it a tie. The upper and lower, that's literally the upper and lower triangle of the adjacency matrix. So it's I greater than J or J greater than I. So if your data is sorted in a meaningful way, these would be useful. I suspect for many of us, our data won't be sorted in that way. But that's probably there. You can also do some really funky reparameterizations of the terms themselves. Any really sort of formula you can write that's sensible you can put in here. Most of them I wouldn't be able to understand, and I suspect many of us could write formulas that we couldn't understand. So I would go into this knowing what you're going to do. But the common one is to sum and combine group effects. So I can say, let's look at, I can combine race and gender for a subset by combining and nesting these full rings. Some section. So you can pull out elements. To my way of thinking, whenever you get to many of these kinds of, so when you get to many of these kinds of reparameterizations, you might want to ask yourself whether or not it would make more sense to use a more flexible term. So there's a whole set of terms for mixing matrices, for example, which I think are probably often easier to at least communicate than sums of categorical attributes, but they are slightly different in how they fit. So again, as we've said thus far, make sure your theory is good, and so why you would do it. But that's there. You can also extract subgraphs. And so you might do this, and you just by literally pulling out and just fitting your data to a subset of the graphs. But the most common reason to do this would be to essentially apply some set of terms that you're going to effectively layer onto the graph as a whole, right? So in this case, what they've done in the example is they fit this Sampson data, the Sampson-like data, with an edges and a mutuality term. So that's just whether or not we have a simple density term and whether or not there's any reciprocity. So that's what's being fit there. But then we say, let's also then fit a second version of this model just to, not a second, but let's add to this model, right? Add to this model another set of coefficients that describe edges and mutuality only among the Turks in this set. Right? And so what this says is this is what the coefficient would be for non-Turks, for the density and the reciprocity, and then this is the additional density you would see for the Turks and the additional change in reciprocity. Right? So this is a nice way to get interaction terms for some of these kinds of features. Go ahead.
So I've run a variety of programs, and I know that these are, or I shouldn't say I know, I think they largely are dependent upon it's been a few years, the exogenous variables that we put into the model. If we don't have a lot of those, then that can make it very difficult. But like the group component here, do they have to be separated by group? I know there's a multiplex option within ERGMs to do an R, but does the group assignment assume that people cannot, or observations cannot exist within and out of the group?
No, it does not assume that. So the group is, in this case, the group is a variable in the, it's an attribute of the data set, right? And so.
Perhaps like if someone exists within Turks, but also outside of Turks.
So what you're just doing is you're describing a cross-group interaction, right? And so that sounds to me, if I'm hearing it right, that sounds to me like you're saying that it might be that, that sophomores interact differently with juniors than they interact with other sophomores. And so that would be something where you would fit it with a mixing matrix parameter. Or you could fit it out with an interaction to say that my grade differs by my gender, right? And so the effective grade differs by gender. And it turns out now that you can, in fact, I have that coming, you can now exactly specify some interactions for exogenous variables. I'm going to take a small asterisk on the sentence you said that says that the models depend on exogenous variables. They don't, right? The exogenous variables, the things that are out in the world, yeah. No, you said it right. Right, but I'm going to say that that's not a feature of the model. It's a feature of your network. Right? And so your network might depend on the exogenous features that are going on in the game, and the model's just going to fit what you tell it. And so if you didn't collect data on the things that are driving your network, then you're kind of out of luck. So that's just one of these niddly little model specification bits that I want to be clear on. All right. So you can also specify different kinds of features, right? So these kind of subgroups is another one I just did in one of the high school cases, right? So I said, let's do it. Let's see if there's a difference in gender on the same kind of model in a high school network. So again, we have edges and mutual, and then we add to that for the difference for where sex equals 1. And we can see that there's a slight difference in density. I think ones are males in this case, and where they have somewhat lower reciprocation rates than we would expect overall, it's not statistically significant in this set. So that's how you would interpret this kind of model. This is, I just want to be really clear, this is really cool. So the ability to do this is something that when I first came out and I was presenting these kinds of models on adolescents, and I would say something like, transitivity matters. And they'd say, is that the same within sex as it is across sex? Do boys nominate girls the same rate? Is it the same, within race, between race? Like, I don't know, right? Now we can know, and that's kind of cool, right? Please.
So if we use the term like sex equals 1, and then does it represent only for sex 1 group, or we have, so if I want to know about sex 0's group, do I have to put in?
Yeah, so what I did here is this model effectively assumes that of all the possible dyads, in this particular case, sex is only 1 or 0, right? Or 1 or 2, I think, actually, in this case. And so what this model is saying is that there's one coefficient that defines all dyads that are 2, 2, 2, 1, or 1, 2. So all 3 of those sides fall in here, and then the 1, 1 dyad falls in here. Right. Now, what I could do instead is then say I could add another subset for is equal to 2, and then this would describe the cross race, the cross gender ties, and these 2 separate formulas would be for the different within ties. Now, if I really wanted to do that, I could also just say mutual parentheses diff equals true, and that would give me a separate parameter for diff equals true and variable equals sex. and that would give me one mutual coefficient for within males and one for within females, and the comparison group would be between males. If I wanted to say that let's compare all possible dyads to just the female-female dyad, I could use the mixing matrix parameter and specify that as the reference group.
And I have one more question. If we use design our model like this, and there are some overlapping types, like just action mutual covers all of the relationships, like 1 to 1, 0 to 0, and 1 to 0. But the second part is about one-on-one relationship, so there are some overlapping.
Yeah, exactly. That's why these are additive coefficients, right? So in the log odds of a tie between of 1-1 is the baseline set plus the boost you get for here. So it's not separate. You could model a separate model, but that's not what this be by the virtue of this. Like that's what the plus sign means, right? So the fact that I put them together, that they're there. What this is doing is it's saying I'm assuming a homogeneous effect within all other categories of sex other than the 1-1 ties. Does that help? Now, what's nice about this is that you can then specify, you can pull out subsets of the matrix and fit anything within this model that you would put in a regular model, right? Now, they might be harder to converge and harder to do, but it sort of gives you a huge amount of flexibility to say that by attributes, I have essentially non-homogeneous coefficients. And that's been one of the complaints of the ERGM models, is that they assume the coefficients are the same across all the elements of the set. And we, sociologists love to complicate things, and we know that that's probably not true. So we go the other way. All right. So there's lots of other things you can do with this. Like let's say you can subset a graph. You can constrain the sample space of the graph. So you can say instead of just fitting a model to the class of all possible graphs defined by this, the set that by the terms in the model, you might constrain your graph, your sample space, that denominator of the normalizing constant, to something other than just the set you have. Go here warily, right? Don't do this if you don't really understand what you're doing. But the most common, by far, the way that people do this is that you would constrain the degree distribution. And so there are a couple reasons you do this. One is because the degree distribution drives a huge amount of the world that's out there in the volume. And so if you don't understand where your degree distribution comes from, it might be, I'd just give up and fit it. Better reason for that is because you probably have survey data where the degree distribution has been constrained by the survey design. And so you want to take that into account. You don't want to try to compare your data to a class of data that could be generated in the wild that has degree distributions that are just impossible by your survey design. So it's a great way to constrain that. But it turns out that another reason to do it is that if your survey design or other kind of data design generates structural zeros, if there are things where the network can't change, the zeros that you observe in the data have to be zero logically, or the ones have to be ones logically, then you can fit that by putting these kinds of constraints in. Any other words of caution there, Carter?
It's like if there's one thing, many of you are probably about black number data, and if there's one thing I can force you to do, please do not censor the data, right? Do not have a design that says name up to 5x. Don't ever do this, please, because you will screw your data. And then if you are going to do it, please don't tell people you're doing it. So if you must censor, don't censor. But if you must censor, don't tell them where you're censoring, because you create a demand effect. If I say, if I tell you name up to 30 best friends, and you're gonna rack your brain to come up with numbers, and if I say up to 3, right, you're gonna get very different answers. So there's unfortunately a lot of data that's been collected that has these constraints, and it screws up the data in lots of ways that I can spell and I won't. Please don't collect it. But yes, given that you have it, right, these are things to do. But yeah, I think that's exactly the kind of case where it makes sense to do them, or where there are groups that literally logically cannot be tied to each other. It doesn't make any sense. Bipartite networks are a special case, in fact, that we aren't coded. But then it makes total sense to do that. I would exercise some caution about the just constraining your degree distribution, for instance, just because you want to. if your model is not fitting at all and you can't get the distribution right, then fixing it is sort of a straight, the coefficients will mean the same thing when you fix the model. And so you have to be very careful how to interpret a model like that, or if you fix density. And in fact, sometimes people do that, it's because they're kind of trying to do something they shouldn't, and this is a way to get away with it. And actually even some proud members of our community who should know better than to do that. If the model just won't fit and won't work, that's nature trying to tell you something. It's telling you, and I think you put it really well, your theory is wrong. And you may really believe in your theory, and you may think it's got to be right, because I'm so smart, but the data is telling you you're wrong. So listen when the data tells you you're wrong, you're misunderstanding something. And you're not going to get everything right. Models are models, they're not real, and you're not going to get everything perfectly right. But if you're really fundamentally not getting the distribution right, really you should be going back to basics and thinking about what's going on in this network, and what am I not getting, and why not. And I think you're better off trying to come up with a model that's a better approximation and racking your brain to do that, rather than just saying, well, by fiat, I will declare the degree distribution to be the observed value. Then I can never be wrong, right, by choice. I'm not saying you would never encounter a circumstance where that might be a good thing to do, but I think in most settings, I would be cautious about forcing the model to give me back the data that I gave it, because then what the coefficients mean will not necessarily be clear. Unless, exactly as you say, unless I'm in a situation where that feature really was constrained and it did have to be that way, and it's not the parameter's fault. Right? So constraints are very powerful. There are a lot of really good uses for them. But yeah, avoid abusing the power, right? By just trying to say, I'm just going to fix the model to make it give me my data back so I can brag about my data. And if you're going to do that, just fix all the cells. Now you have 100% perfect prediction, right? Constrain all of this ties to be exactly what they are, right? We don't want to go down that road. So that's my caution.
All right, so yeah, so you can get So there, yes. And over beer, we can discuss when you might do it otherwise. But usually when I will constrain the data when I'm making data up, right? So when I'm trying to simulate data with something, I will do that. But usually that's an entirely different set of processes. I'm not trying to estimate anything at all in those cases. And so you now have the opportunities to add interaction effects in ERGM the same way you would in any other linear model in R. So you can use either the colon effect or the star effect, and you can just literally go through and add it, and it'll do the kinds of things you expect it to do. So in this case, we have an edges term, a node factor, and a grade, and that interacts with the node factor by sex. It puts in both the base coefficients and the interaction terms. And the beautiful part about this is that you can now do this, right, in the way that you would like to do it. The difficulty of this is there are some things you can't quite do yet. And so, for example, it doesn't by default give you interaction terms involving the non-dyadic independent terms. I love this line in the tutorial. It tells you what it's doing because of the way the sufficient statistics are summed. It says, attempting to create interactions involving these terms will create an error by default. But if you want to do it anyway, you can turn off the option, right? So I thank you for that. I mean, that's nice, and that's very trusting to the rest of us. But be really cautious if you're going to go do this, because you probably don't know what it means. I don't know what it means. And the reason is, I think that especially for things like the GWESP terms or other kinds of terms, these non-independent terms, the sample space is just really complicated to figure out there. So I think that my guess is most of the time with some careful parameterizing of the subset sort of features, you can probably get most of those kinds of things you would like to get without having to use the formal interaction term set. What else to say? All right. That's the bit on the new syntax. There's more there than I have time to go into, but I think it's worth just putting it out there. Now I just want to run through a handful of sort of fun things you can use these models for that you might not know that you can use these models for. And that's sort of what the flavor of the next few sets have. So the first is you can do value ties. And you can do more than just ordinal level ties. You can do sort of full set of value ties. The new work, and you'll see there's a wonderful tutorial that the group put together, Stanton already put together on value ties, and it includes a whole discussion of a series of the distributions that you can fit and the ways that they can be fit and so forth, and I'll talk a little bit about those. The key element is that the data structure is designed in order to fit these models of a tie matrix and a tie attribute matrix. And so the values are attributes on the edges, right? And so you still have to feed it an edge list, which is, or conceptually you're feeding it an edge list, where you have ego I is tied to alter j, and then you say, what's the value of the alter j tie? And to use the valued ERGM models, you need to specify some kind of an attribute name that is fit. Now the name can be whatever you call it. We call it nominations here, but it can be, it can be boo or whatever it is you like. So then it turns out in order to do this, you have to tell it, you'll notice that the equation now changed just a little bit. We added this critter up here. That's your reference distribution. And so the reference distribution is the thing that sets sort of what kind of model it's trying to fit, right? And so you need to specify, you don't need to specify this in the binary case because it's the default. But if you're anything other than the binary case, you have to specify what that is. And so there's a series of different distributions that can be fit. The ones that are obvious that we will end up using probably more often than not are the binomial where you have a number of trials. And so if you can fit, if you know that the number, your dependent variable has a certain number of events that can happen, then you can set that here. And so you'll see that in an example. And the other are different types of count models, right? So we'll end up using those a fair often. I don't know if, I don't know how often other people use the other ones, but they're there as well. So how do these models set up? So what you want to do is that the language changes a little bit, right? So you're fitting this kind of a model up here on the monastery data, where you have the opportunity to be observed 3 times, and we're going to ask how often do you actually get observed being tied to each other. You munge your data around to get it in the right format. And then notice we've changed the intercept term to be the sum. So that's just a change in the diagnostic. And then we're doing whatever sort of feature you would normally fit. You do that. In this case, we do the form is equal the sum because that's telling us that we're doing a valued tie. You can also do non-zero, which would force it back to being either there or not. And I don't know if it gives a limit for non-zero would be like literally anything above 0. You could probably also do. It's a tangent. I'll go off on that. You have to tell it what attribute on your edges is your modeling. And so this is what I said before when you have your attributes here, right? So this is the attribute set. You have to explicitly reference that in the model, and you have to tell it what binomial, what distribution you're using. And so but once you have that, it's really kind of, it works. And this is really kind of cool because it gives you a chance to do all these models on different types of counts and so forth that you get, and you get the kind of model you might expect. And so there's strong evidence for baseline homophily in the different kinds of groups in this set, which is not surprising because that's how the data is set up. This is the non-zero term here. That's right. This is the zero inflation model. So it's often the case. Is that the model I specified? No, I switched models on you. Yeah, there we go. So the non-zero term here is oftentimes in count data and other kinds of valued data on networks, the network is still sparse. So the underlying adjacency matrix A tied to B is still a sparse matrix, and so you have many fewer non-zero cases than you would expect by chance, given the rest of the sum of the values on the edges. And so you want to figure out that you make sure you adjust for that. And so that's what this does. It tests whether or not it's effectively a zero inflated model. And so this is telling us that we have fewer non-zero cases than we would expect by chance. So there's an excess of zeros in the data than you'd expect by the model. And so intuitively, I think of this as effectively a data construction constraint kind of thing. So it's in many ways just like the intercept. It's just separating the intercept out in terms of the distribution of the ties across the set. You rarely have a reason to interpret this substantively. But it then gives you an accurate representation of how you interpret the rest of these, or more accurate. Please.
So when we're writing the count model, it's important to make sure that it's a good fit. So like with the song, to make sure that the distribution of fitting with the data binomial, when you're doing things like the regression side of the house, it doesn't always converge because, depending on theory, depending on the data, whether or not those zeros are meaningful and whatnot. Do you recommend assessing the data to ensure that you're not just throwing, you might have a count variable, but it might not be appropriate to run a count equation in an ERGM on the data if it's like the data doesn't.
Yeah, I think that what you need to do is ask yourself whether or not which of these distributions are going to fit best. And so you have the binomial, the Poisson, you have the geometric distribution, you have a handful for continuous distributions that I've never played with. I think that you take one of these distributions and add to it the ability to do zero inflated, you're going to be able to find a pretty good bet to most of the kind of data most of us fit. So I think that from a substantive standpoint, the tool should be able to handle what's there. I guess I've always considered I don't know that there is a marginal test that you can do on these edges other than fitting the model directly.
Yeah, it's so there's a lot of intuition from the linear case doesn't carry you through very well once you start getting into this case. So those reference, we're calling reference distribution, they're really reference measures because they're a piece of distribution. They kind of determine how the model, what the baseline behavior of the model before you get anything else. So if you have a Poissonian reference, it sort of says if you only have independent terms in it, it'll act like a giant Poisson, an inhomogeneous Poisson model. So if you just look at the margin distribution of your data, you might say, oh, it's really skewed. That doesn't mean that a Poisson model won't work well because, of course, that's marginalizing all across all the covariates. So you compare it as a conditionally Poisson. But now once you start adding dependence terms and including, zero inflation, other things, right, it's no longer acting like a Poisson model. It has the reference distributions like a Poisson, but it's now converted into this much more subtle, complicated thing. And so that means the simpler references go a lot further than you think they will because you have all the other things going on. But it is also harder to assess distributional shape issues. That's a frontier at this time, I would say. The best thing you can do, as always, is simulate the model and then look to see if it's adequate. That is it reproducing data that are simulated numbers that look like your data and in the ways you care about? And if the answer is yes, then it's working. But otherwise, it's very hard to have any very trivial heuristics at this time. And yeah, there's a lot we don't know, and especially when you start getting into high variance count distributions, which actually, my student Pangwan been working on this a bit in migration settings where we have wildly huge skewed things. That has considerations for the model as well. Although Poissonian references often work very well for those. Once again, you have other terms of the model. So that's just something we're still learning a lot. And in general, I'd say value ERGMs are very much a frontier. We can fit them, but almost no one has. So this is a great area. You're looking for something where people know very little, and you want to go do something and make headway. This is pretty open right now. There's a lot we just don't know yet.
All right. So the value ties. One of the things that just to keep in mind. I'm not going to go over this in great detail because I want to get to a couple of the others. But the notion of reciprocation, you have to think a minute about what that means, and this is true for all your kind of past statistics now. So is it that I respond at the same value that you respond to me? Do I overcompensate? Do I undercompensate? Do I do anything at all? So you need to think about what that means. And so this is what it's a whole series of forms that go onto the mutual term. So the mutual term isn't just there or not, but it's how often do you do. The sum is probably, I'm guessing, the sum of the min are probably the most common that are used, but they apply to all of these features. I use the min here, or you use the min here. I don't remember who did this one. Similarly with the cyclic path, you need to think about the ways in which you combine the two paths. So we have a directed triple, for example, where we're going from I to K to J. And so we need to figure out whether or not the transitivity and cyclic weights have these three-part functions. And these three-part functions correlate to what you think this kind of path should be. So is it, given that there's a strength of the two path, so from V2 is the two path, the first term, how do you count that? So it's the smallest of these two values, the largest of these two values, the mean of these two values, or if you think of then about the underlying closure path, and then given those things, what's the strength of the IJ tie? So all of these fit in together. So on these products, we used to be able to just fit a GWESP term with one thing on it. Once you get to a value configuration, you now have to think about value patterns. And so it's like, in many ways, it's, yay, I got it, crap, I got it, right? It's like, so your theory has to match the underlying data. And so now most of our sociology theories probably don't do this. And so you're going to have to spend some time thinking about, which of these I fit. The nice thing about the manual again and the software team is they've done a nice job of telling us at least which ones are the easiest to interpret, right? And so I don't know what it means, but this is kind of what it does. And so I would certainly start with that kind of set. But in this case, this min-max-min pattern is telling us that there's fewer transitive closure ties than we would expect by chance at this specification. And this is telling us there's also fewer of those. Net of the mixing parameters and the popularity of the nodes. They're not statistically significant in this case, but that's how you would read those types of things. Okay. There's a whole series of ways you can also now do value ties in latent net. So if you want to do that, those are in there as well. So that's the ERGM with a double M on it there. You can also do rank models. I'm not going to go into detail on this, though I spent an inordinate amount of time learning these models over the last couple of weeks. And they're really kind of cool. There's if you happen to collect your data in ranks, it really raises a series of interesting pieces because if each person ranks every other person, then things like marginal density distributions, things like that go away. And so it really becomes, we no longer, like a lot of the volume features that we sort of think of intuitively in these network models, they don't matter because the volume has been fixed by the ranking process. And so, so then you're really thinking is my ranking consistent with other people's ranking? Does a target's attribute increase or decrease their rank? I'm actually excited to use these models on some of the hierarchy process sort of things that Ivan Chase and the animal people have been working on. So I want to kind of play with that. But I'm going to skip over it for now. The other thing that you can do now natively, which we were never able to do before, is analyze multiple networks simultaneously. And this is really kind of cool in an HLM-like type framework. And so you can I've taken 5 village networks here. Each of these networks is about 400 or 500 nodes, if I remember right. And so maybe it's not quite that big given what I'm at there. But then you can add there's a size right there. So you just add them all into one large object. So you create a network, which is a construction of the list of all your networks. And so in this case, I have a multiple village network object, which includes all of these villages. It's not actually 7, it's 5. I don't know how I did that. But then you now have this single object that's built in, and you can model it now as a function of the kind of things that you would want to do. And so what I've done in this case is I fit, again, a very simple model where I've said that for this network feature, it sort of bounds the elements that are occurring. Do I have it there? There we go. And so I have a baseline set of edges, and then I have this thing called scheduled caste. So is the person, I'm going to partition my network by whether or not you're a member of a caste. All of these villages are in India, and I'm going to let that differ by which caste you're in. I use the MPLE here not because I recommend it, but because I was late in putting together my slide and I wasn't going to wait for it to converge. So that's really so you're going to see MPLE here a number of times in the call out. I'm in no way recommending that. This is purely for illustration purposes. I just wanted it to run quickly. And so what you see in this case then is we have sort of the same kind of model that we would expect there. There's nothing particularly interesting going on in this set. But you can also then specify these things to have some, not just that they differ across the setting, right? So that we have the edges and mutual are set to be combined across the set. But now we've also specified some village level feature that modifies the parameters that you would get. So you think of this as a cross-level interaction if we're used to HLM kind of terms in an interpretation sense. So what this says is that there's a density term that we're going here, but we're saying that density term is conditioned by the size of the network. And that should be true because we know that the average degree stays about the same, but the denominator goes up. So of course the density should be highly dependent on n, and in fact it is. The bigger your network, the lower the density. That's almost mechanical, but we would expect that to be there. But this is a great way to add sort of a feature of the network. Now, mutuality, I don't have a strong theory for why mutuality would necessarily be increased in large networks, but it turns out to be the case in this sample that we get higher levels of mutuality in the larger villages than in the smaller villages. Right? Notice that I separated this in parentheses terms allows you to effectively decide which elements your village level things are going to apply to. So in this case, I was willing to assume that there's a conditional difference in the ways in which the volume features of the network differ by village size, but I didn't think it would affect the underlying probability that cast members have ties inside or out in small villages, so I didn't test that. And so this is a homogeneous parameter fit across all the sizes of the villages. And so in this case, we find that there is strong caste homophily, that the scheduled cast members are much more likely to interact with each other, and the non-scheduled class members are also more likely to interact with each other, though the magnitude of those coefficients is somewhat different. All right. You can keep doing this with lots of different things. Here I said, well, maybe it's the case, though, that your scheduled cast homophily is more likely depending on the number of kids in this village. So the number of families that have small kids might affect the likelihood they go to the same school or some such. And so we find that the more kids, the more families with small kids there are in this village, the lower the level of segregation by caste. So that's kind of a nice feature. All right. That was the world's fastest introduction to lots of networks at once. That's all I'm going to tell you about that. Questions, comments, thoughts? It is a really cool feature. I haven't tried to actually estimate a model using the full estimation feature on a really complicated model across all, say, 300 Prosper schools. So I have no idea how long that would take, but I think it would be a good idea. Please.
Yes, so this is clarification, most likely not understanding completely yet everything. But is it possible to figure out how much of the residual error between the villages versus the villages, like you would in a regular? So is there a way to figure out, like, okay, most of this difference happens between villages rather than within villages?
I don't know the answer to that. Is there a way to parse that out?
You have to say what you mean by error. What do you mean by error?
Or I guess
This is not an LLS.
Right.
What do you mean?
I guess I meant like the analogous version of that, which this is where I'm going. But
I mean, what you could do is you could look at the conditional likelihood. So you can see what the conditional deviance is, and you can look at conditional likelihood. One of these, how homogeneous that is. Although that's a little tough to normalize, because versus larger villages will be intrinsically hard to predict because they're bigger. So you have to figure out a reason to normalize that. But that would be the direction you have to go. Probably would make more sense instead you can actually substantively target something that you care about knowing, and then do simulation experiment to see how accurately am I reproducing this feature across all the villages, and do I do a good job? Are there villages that I'm not getting mutuality right? Are there villages where I'm not getting some other property right? And yeah, you do have to interpret things jointly too. So just one quick, just to add one thing about your mutualities. Gave that example. You have to be a little careful because when you interpret that, remember it's being interpreted along with density. So here you have to make sure that the density is falling because the mean degree is staying about the same. And the fact that you got that coefficient almost exactly -1, which is actually really beautiful. Because -1 means exactly the mean degree is the same. Of course, I wondered how they put the data and whether that's hard.
It was not. This was an unlimited nomination set, so that's good.
That's actually brilliant. That's like telling you, man, in that population, that mean degree is really constant. But now, if the mean degree is staying constant, and in a big village, the density is going down. So that would mean the edgewise reciprocity should go down as well, because if I'm nominating K people, and now there are more people to pick, the chance that you and I would both pick each other is going to go down. So the only way to keep mutuality constant is for mutuality to go up, and it has to go up exactly by an amount that offsets the amount that the density would go down. And so what you should see is a coefficient of 1 for your log n mutual effect, but you don't.
Yep.
So what that actually says is it's less than 1. So what that actually says is that the large villages are less mutual, all other things being equal, than the small ones. They're more mutual than they would be if it was just, we're just gonna nominate each other, and we're each nominating K. But there's a diminishing kind of return in a sense. So to some extent, there is a tendency for mutuality not to scale in a way to exactly offset. It's not constant as in, which in many networks we do see that the reciprocity can stay in K. So there's a lot you can read out of even very simple coefficients. But one wants to remember, they all have to be looked at vis-a-vis what's going on in the other coefficients.
Tom.
This might overlap a bit. When you're talking about, doing an ERGM of multiple networks simultaneously, like, say you have something like at health, or like it doesn't say networks across the country, but right, the proportion of, I'm thinking like weighting, essentially, right? That some networks that you might collect might, be more prevalent kind of in the broader system of these networks than others, right? Is there any way to account for that as you're doing these things, or is the assumption here that basically all these are all equally representative cases of networks?
I don't know the answer to that.
As of right now, I don't believe that's
Yeah.
done.
Yeah.
There's weighting and currently. In theory, you certainly can do that, although there are some things that one would want to work out for standard error correction. But yeah, and I mean, unless the only thing to think about is, I don't know whether in some of the more recent tools that I know Pablo's been doing to do inference from egonets and other like local samples, right? There, you have to do some intrinsic weighting, at least if you're using design estimator to get the statistics.
That's what Moody is.
He may have looked at that. I mean, that gets us down into the weeds. I don't want to go there.
Yeah.
But there are some of the longer conversation. But in general, there are a lot of this is a really exciting direction. There's a lot of stuff that we can now do where you can take sample network data and you can do inference from that to a population, including here you have a population of networks, but you can also get one large network. And so if you get local data, egocentric data, RDS data, whatever, you want to do inference on the larger network. We have principal ways to do some of that stuff, and that was what you mentioned, Martina, earlier, the huge driver, the visionary behind that project at the beginning. Martina is concerned very much with HIV and being able to model sexual contact networks in large populations to look at things like HIV. And there's no way to do that without sample data. Yeah. And so to be able to figure out how do we sample data to local data to answer global network questions has been kind of a big driver. And we're now at the point where we can start to do that. And some of these kinds of reweighting questions or whatever are essential to doing it. But the essence of it is that because of the way ERGM works, it depends on these things called sufficient statistics. If you get the statistics right, you can model the network. Even if you don't see the networks, you actually have to see the network. That's just a convenient way of getting statistics. But you can do it through sample. But there are challenges that come in with error. So that is an area where there's a lot of progress, but there's still a lot of things being worked out. So I don't know that all that's implemented at the moment, but in theory, yeah.
So we talked about this a bit. It's come up. Is there's now the ERGM.multi package, which allows or function inside the StatNet suite of packages, which allows you to model multi-layer networks. The multi-layer net it's a somewhat constrained version of the overall general notion of multi-layer networks that some people have talked about. So, in particularly, there's, as near as I can tell, there's not a good way to model between layer ties. And so there's each layer, and you can have multiple layers, and each layer is linked by the IDs of the nodes. And so you have this effect in which there's a layer-specific feature. But if I want to do and you can do lots of node-specific between-layer paths. So I can say, for example, that a friend of a coworker is also a coworker. Those kinds of different layers. If I have a coworker layer and a friend layer, but to say, if I have one layer of parasites and another layer of humans and another layer of organizations, I can't say that this parasite was found at this organization where this human worked. So that kind of set needs to be treated as a k-partite network within its own layer, or treated by edge attributes. At least as near as I can tell, I've never used one of these models. I've just wanted to show you that it's there. Yeah.
describing would be a K-mode network,
Right.
right? You've got, like say, you've got parasites, individual humans, and organizations in which they work. Those are three different modes, different kinds of nodes, and then you might have different kinds of relations on those nodes. So we would say the layers are the kinds of ties, and then the modes, right, are
Right.
the kinds of nodes.
Right. And I think that's, yeah, no, exactly. This is but if they go out and Google multi-layer networks, they're not going to get the constraint that we would say of a layer is a relation. So,
The terminology in that area is sloppy.
yes. Right, exactly.
So, in comparison with the generalized ERGM that says we get edge value, does that feel like a different way of getting at the multiplex media stable relation?
Well, what do you mean by generalized version?
There's a ERGM.
Yeah.
Wait, but there's problems.
Well, okay, so if you're saying, I think you're talking about the thing I'm thinking about. Yeah, those are, I would call those copular ergoms, but anyway, they call it generalized. I don't like that term. But, so that's a way of doing a standard ergom where you have a non-parametric edge weighting distribution. So you allow the edge weights to be non-parametric, and it's really using something that in this conduct is called a copular model. And actually, I think the author basically reinvented copulas. The paper was way ahead of its time. It's actually not a very recent paper. And I think it didn't get much attention for a long time because it was sort of like, it was way ahead of what we're thinking about the value stuff. So very creative work. But that deals with case where you have continuously valued ties, and the distributions could be all kinds of strange. And you want a non-parametric way to model that interaction without having to be able to specify the distribution of the tie weights, because they could be continuous and they could be really bizarre. And it's very flexible in that way. But this is a different question. This has to do with constraints on the different kinds of nodes and different kinds of relationships, and you want to be able to specify that how parasites infect humans is not the same necessarily as humans working for organizations, although if you're working for an organization, you might think so. But we want to go treat those as distinct kinds of things that have their own rules. That's a very different question than talking about the strength of a tie, which is what that
But the beauty of the multi-layer version of the ERGM that is here is that it does allow us to model the patterns of relations, of different types of relations across a set of nodes. And then this, I would typically think of as multiplex kinds of questions. And so does coworker and friendship or family and co-work and adjacency and these kinds of things, how do they relate to each other? The one thing that you do have to do is to generate a multi-layer network. And so at the end of the day, sort of working backwards, the layer function creates on whatever sort of single layer or multiplex network you have, you take each of the relations that are part of an edge attribute, those become the layers on the network. Now it's in the case here that what we've done is we've at least in playing with it briefly, and I am the world's worst data munger in R. I'm just going to step out and say that together, is that we found a bit of for me, the trickiest part was recognizing that these edge attributes need to label extant dyads, as opposed to having a multiplex. So if you do the fact that this multiple equals false is what threw me for a long time. So I was it wouldn't take an edge list, for example, at least the way I had it specified, with multiple dyads of different types. But if I had one dyad with multiple attributes, it read it just fine. And so, again, that could easily be my error, but this sort of version of first effectively making it a wide attribute on the edges, so you have a single edge list and then zeros or ones for whether or not that attribute applies, works fine. So once you have that, you create your multi-layer network object. This is the world's worst graph of a multi-layer network. There are 3 villages in this case, or 3 relations essentially in here with the nodes repeated. Except that if you squint, it kind of looks like the StatNet logo, and so that's why I put it up there, just because I thought it was fun. The other thing that's really been clever, and there's a tour de force that Pavel has in using this on the Lagaza lawyer data, which has like 8 different relations in it. You can specify combinations of layers in really fun ways, and so you can take the and, the or the exclusive or, and figure out that a parameter applies to this relation and that relation jointly, or this relation or that relation, or this relation and not that relation. And so it's a very nice, they call it a layer logic syntax, and it's really powerful. It's a little complicated, and I don't pretend to understand it particularly well, but I think that if you're going to do these kinds of models, it's worth getting in and doing, and it has lots of chances to do that. There's also a whole set now, a whole host of layer-specific or layer, of parameters that match layers exactly. The one term that's brand new, at least to my understanding, is this CMBL, which is Conway-Maxwell-Biswell binomial, dependence. You can think of this as the multiple correlation across all your layers, and so this lets you see essentially the likelihood that a layer is dependent, the layers are interdependent, and then you can also do edgewise dependence on them. So, for example, this is just using my little one village with 3 relations. I want to ask, is there an association between the health, the free time, and the finance ties? And it turns out that we do find that those things correlate more higher than you would expect. Now, you can also specify that as a function of, that's not my data, you can as a function of whether or not I want to say that this layer logic, I can say, is there an edgewise dependence between the health and finance network, or an edgewise dependence between the free time and finance dependence. Here I've just specified all possible edgewise dependencies there to see what's effectively if they differ. The density is pretty similar across the 3, and so that allows you to see what's there. And so we see that, for example, the free time and finance tends to be more associated with each other than health and free time, would be a sort of rough way to look at that. It turns out there are equivalents, just like you have to think carefully about what a mutual term means in a valued network, you need to think carefully about what a path structure means in a multi-layer network. So now we have a baseline parameter, so with the way in which this thing is related and which different layers you can go through on the other set. And so there's lots of different ways to specify this. I wasn't able to get an example to work in time, but there it is. So that's, I'm now out of time. I've gone over to where we should do into our coffee set. So I will say that in the slide deck, there's a couple of other features of models. Peter Hoff and Alex Wolfowski have a model that is this additive, they call it the AMEN model, which I think is my favorite statistical model acronym yet, because I'm always praying that these things converge. And so this gives you a chance to fit different sets of effects, including, at the end of the day, a latent space model is what's being fit over here in the set. And so it's a very flexible model. I haven't ran it in recent years, but the last time I did, which was many years ago, it was very slow, but I'm assuming it's gotten faster as well. All right, so if you want to think a bit about the dependent variable side, we're going to do more of that later on today. So I'm just going to leave the slide deck to your perusal, and also happy to talk to you about it there. And otherwise, just questions or comments before we break for coffee. We've jumped in a few times already, so please.
Maybe this is basic. I'm just trying to clarify my brain. We have, like, say, classrooms inside of a school, and we recently think that the same types of behaviors are happening in each of the classrooms. We would use a multiple network instead of a constraint in classroom tie-only system, or are they essentially? Well,
my intuition would be that you would use the multiple network, and so we'll see if my intuition's any good. But my intuition would be you'd use the multiple network feature, and you would estimate it that way. And then if there's any feature such as size that might have, or that would have these constraints, then you can set that as a network level covariate that then adjusts the others. Whether or not you could fit it with a series of constraints on the off diagonals and things like this, and one big block matrix, maybe. I can't imagine that would be easier than doing it this way.
You theoretically recommend multi-network.
Yeah, that would be my intuition. I mean, that's why they built it. So.
It's doing the same thing. That's actually what it does.
Yeah.
So the dark secret is that, what's it doing under the hood. It's all sticking it in one giant network and putting block diagonal constraints on it. So you can do that by hand, and in fact, you should find that if you do it by hand the right way, you get exactly the same result.
I was kind of thinking that, but I was like, I don't know.
Yeah, that's actually what it is. I mean, it's kind of disappointing when you discover how
Pull back the sheet on that.
Yeah, I know. Well, and for years, there was a package I wrote floating around for years that did this. It was a very drafty package. And, you know, people would every now and then be like, I need this functionality. Like, well, okay, this thing barely works, but here you go. And it did it. It just did it in the front end. It did exactly that. And so Pop has a much nicer version, which was implemented. So it's doing in the back end. But it's doing the same thing. It's just that it has, by having integrated it, it makes it much easier to do these things that like Jim was showing where, I want to allow some things to be pooled and some things not to be pooled and that kind of stuff, which is a nice thing.
Awesome.
What we don't have right now, well, there are a number of things we don't have. One thing we don't have right now, though, that is relevant to that is we don't have regularization built into that. Some of us have our own dark magic versions that do have things like that, but in terms of stat itself. And so, sort of hierarchical modeling and partial pooling kinds of things right now, we don't have that built in so much. So you can do like straight pooling and you can do direct partial pooling, but we don't have some of the other things.
Please.
When considering like having multiple networks, is there a way to account for differences across the networks? Like one of my networks is more missing than the other, and so is there a way to like downweight or upweight, or is that accounted for in any way?
This is, I ran out of time. I'm already over time, but the beauty now of the entire new StatNext set is that treating missing data is transparent. It's a native function of the model. If you have your edges are NA, it does the right thing, which is awesome, right? So that really is great. So a lot of the work that we had to do back in the day of essentially, sort of figuring out ways in which we could impute data from these kinds of models is now just done directly. It's using the available information. So what that means is your old habit, my old habit, most of the field's old habit, of listwise deleting all of our edges and making sure we have a 0-1 matrix that's without any NAs in it. We need to break that habit and leave the NAs in and put it back in. So that's the set. Awesome. Grab some more coffee, and Tom, you're next, right?